Okay, now we move on to the second part of the phase shift oscillator. It is still the oscillator circuit, but we look into another type of oscillator with the same topic learning outcome, where you should be able to describe the operation of phase shift oscillator, analyze it and derive the transfer function, draw the waveform related to it, determine the frequency of oscillation, and how to design the phase shift oscillator. Okay, initially we have talked about this type of phase shift oscillator. Now we move to a similar circuit, but we swap the position of R and C. If you look over here, the C is up there, but this one, it is R, the resistor. So it will give a different frequency of oscillation. Okay, so for this type of phase shift oscillator, we still have the amplifier, which is an inverting amplifier with 180-degree phase shift. Okay, so your input VI over here will be out of phase with the output. Your VI is actually the feedback voltage over here, and this part is your feedback network or the feedback factor. With a positive feedback, it will introduce another 180 phase shift. You have 3 pairs of RC. This part will select the frequency of oscillation, and it is also an attenuator. Your output signal will be fed to this feedback network, and the signal will be lowered, okay, in terms of the amplitude, and it will be amplified again. So there is a closed loop, and this must fulfill the Barkhausen criteria of 360-degree phase shift around the loop, and beta, this is your beta, multiply with the gain must equals to 1. So this is what we'll analyze. Okay, and we just look at the feedback network. Okay, I define a current I over here. Actually, it is the current flowing into the amplifier. This current is assumed to be very small. We can ignore this current because the value of your RA over here must be much larger, 10 times compared to the impedance of this capacitor. With that, we can ignore the current. So we simply have the current I5 over here flowing and I6 flowing through the capacitor. So with that, at this particular node, can say that I5 equals to I6. Okay, now we define the voltage over here Vy and not Y. The current just now is I5 and I6. Applying the Kirchhoff current law, I5 equals to I6. Since I5 is flowing from Vy to Vf, so I can write I5 to be Vy minus Vf divided by the resistance over here R, and it is equals to I6, which is the current flowing through the capacitor over here, which is Vf divided by the impedance of the capacitor over here. Actually, Vf minus 0, so I just ignore 0. Vf divided by 1 over j omega c. Simplify the equation, bring over j omega c on top of the equation, cross multiply with the r. So you have Vy minus Vy equals to j omega rc Vf. Simplified, you have Vy equals to 1 plus j omega rc Vf. And next is at another node, which is over here, the current will be I3 entering the node, leaving the node will be I4 and I5. So using the Kirchhoff current law, I3 equals to I4 plus I5. Substitute this I3, I4 and I5 using the Kirchhoff current law. I3 flowing from Vx to Vy, so I can simply write Vx minus Vy divided by R. As for I4, it will be Vy divided by the impedance of the capacitor, 1 over j omega c. And for I5, it is flowing from Vy to Vf, so it is Vy minus Vf divided by R. So simplify the equation. You have Vx minus Vy equals to j omega rc Vy plus in bracket Vy minus Vf. Simplify it further, you have Vx equals to 2 plus j omega rc. All this multiply with Vy minus Vf. This is at this node Y. And now we move to the next node, which is Vx over here. Okay, the current will be I1 going in, going out is I2 and I3. So using the Kirchhoff current law, I1 equals to I2 plus I3. I1 flowing from this node to this node, so it will be VO minus Vx divided by R over here. I2 will be flowing from this node to the ground, so it will be Vx minus 0 divided by the impedance of the capacitor. Okay, right here, Vx divided by 1 over j omega c, plus I3 flowing from Vx to Vy, so Vx minus Vy divided by the resistance R. Simplify the equation, bring over j omega on top, R cross multiply, you have VO minus Vx equals j omega RC Vx plus in bracket Vx minus Vy. Simplify it further, you have VO equals to in bracket 2 plus j omega RC multiply with Vx minus Vy. So you have one equation at this node. So now we have three equations, and using the last equation, which is your VO just now, VO equals to in bracket 2 plus j omega RC Vx minus Vy. Vy equals to 1 plus j omega RC Vf, and another one, Vx equals to in bracket 2 plus j omega RC Y minus Vy minus Vf. So using all these three equations, simplify, substitute Vy into this equation, you have Vf over here, substitute into this, and so on. So you should be able to get the beta, which is Vf over Vo, and you should be able to get this beta, which is the feedback voltage divided by the output voltage, equals to 1 over in bracket 1 minus 5 omega squared R squared C squared plus J in bracket 6 omega RC minus omega cube R cube C cube. So this is the transfer function for your feedback network, which is beta. And using this beta, we can find the frequency of oscillation. Okay, how to do that? You must satisfy the Barkhausen criteria. So meaning that A multiplied with beta, A your gain, beta is distinct, must be 1, the magnitude, the phase shift must be 360 degree or 0. So you equate this part, which is the imaginary part, to be 0. Okay, equate this to be 0. So you get this 6 omega RC minus omega cube R cube C cube equals to 0. Simplify this equation, you should be able to get this 6 omega RC equals to omega cube R cube C cube. Omega cancel out over here, so you left with 6 equals to omega squared R squared C squared, and this omega will be your frequency of oscillation. In terms of radian per second, it is omega naught equals to square root of 6 divided by RC. And in hertz, it will be F naught equals to square root of 6 over 2 pi RC. So the equation looks similar from the previous circuit, only that the square root of 6 is on top, the numerator. Okay. And at the frequency of oscillation, the imaginary part is 0 because you equate this thing to be 0 just now, right? So now, what will happen to the real part over here? Substitute this omega with square root of 6 over RC. And simplify, you get omega naught, substitute with square root of 6 over RC. You will get beta will equals to minus 1 over 29. So meaning that if you want this circuit to be an oscillator, for beta must be minus 1 over 29, the negative indicating a phase shift of 180 degree provided by the feedback network, and your amplifier is an inverting amplifier. Of course, the gain will be minus RF over RA. This, you have familiar with this inverting amplifier. Okay, minus RF over RA, negative indicating a 180 phase shift. So beta, that's now minus 1 over 29. Beta multiply with A to satisfy the Barkhausen criteria must equals to 1. So the ratio of RF over RA will be 29. Okay, and the gain usually will be slightly greater than 29 in order to start the oscillation. And for this type of phase shift oscillator where your R is over here, the C is tied to the ground, the frequency of oscillation is square root of 6 over 2 pi RC. Different from the previous circuit. And the gain is similar, which is minus RF over RA over here. And in order to design this particular circuit, you must make sure in order to get a sinusoidal waveform, your beta must be minus 1 over 29, where the ratio of RF over RA is 29. And the value of RA over here must be 10 times the impedance of this capacitor. Okay, this is in order to ignore the current over here just now, the I. Okay, so with this, you can design a phase shift oscillator. You can get a sinusoidal waveform, and this circuit will oscillate at a certain frequency given by the value of square root of 6 over 2 pi RC. And with that, we finish with the phase shift oscillator.